How to enjoy.
Sorry.
I said, no.
Good morning. It's a great pleasure to introduce the next speaker who will present the Senior Biometric Investigator Award presentation. It's John Daugman. John was educated in America, but his career was basically in the UK, where he is in Cambridge, the professor of computer vision and pattern recognition. He received the award for his contributions to iris technology. He is the inventor of iris technology, and I think this dates back to 1980s. But since then, he has spent a lot of effort in addressing various scientific issues relating to iris technology and iris processing, iris biometric, and also to technology transfer and other activities associated with it. So in a way, from a politician's point of view, John is the ideal academic because he not only has innovative or had innovative ideas and still has innovative ideas which are outstanding, but also contributes to science and I think he has a large number of publications with total citation count exceeding 20,000. So it's quite an amazing achievement. But on top of that, he contributed to standardization of the technology and indeed to its deployment in the real world and real applications. I think iris technology is being used in many border crossing applications between USA and Canada. It was deployed in UK. And I think it's used routinely in United Arab Emirates, and I think we'll hear about this in more detail from John. John has received many accolades, and they include election to the Royal Academy of Engineering in the UK. He was listed among the top 100 inventors in the time. And there are a number of other accolades that could be mentioned. I think he is in the U.S. National Academy of Inventors Hall of Fame as well. So it's perhaps fitting that we are celebrating the award of Senior Biometric Investigator here today, because John's roots are from this area. I think they are partly Swedish and partly Latvian, so we are very close to his roots, and so it's great to have representation here. So, John.
Thank you. Thank you very much, Joseph, for your very generous and lengthy introduction, and thank you to the organizers for this extremely enjoyable and productive conference. I've learned a lot, and last night was a wonderful evening, and thank you to the awards committee for the award which gave me this opportunity to speak today. It's a great privilege and a pleasure. I want to speak about information theory and biometrics, which I feel is a connection that has been underutilized and underexploited. Although in Didier's last talk we heard a few words about entropy, I was pleased to notice. I will begin just with a short review of information theory, how it applies in a number of different ways to biometrics, to the idea that biometrics is a kind of a channel. That we can speak of biometric identification as constituting a channel. And then I'll move on to particular calculations of entropy and looking at population sizes in which biometrics can be used reliably, looking at face and iris, and then focusing on some particular cases of the kinds of impostors distributions that we get. Especially, my main point will be the fact that in iris, iris is a biometric technology in which all different eyes are approximately equidistant from each other. And the main message I would like you to think about is, what does it mean that all different iris patterns are equidistant, about equally distant from each other? What advantages does that give us in biometrics? So there's a kind of a universal impostors distribution. This is my main theme. Okay, so we can regard, this is a classical concept of information theory, the notion of the communication channel. There's an input and an output. In the case of biometrics, the input might be an actual identity. A person, X, is going into the biometric channel, and an identity may be what comes out from the biometric channel. And for X and Y, the input and the output to the channel, we can speak of the conditional entropies between the two. The conditional entropy of the output given the input is the first concept, and then of course there's also the inverse conditional entropy based on the inverse conditional probability. How much uncertainty is there about what the input was given the output? So you can see that, for example, in Didier's excellent talk this morning, all the questions about likelihood ratio and uncertainty, about the meaning of the evidence and the strength of the evidence and the priors, all fits nicely, I think, into this classical framework of the channel, which is so fundamental to information theory. There are, in fact, several different mappings. I'll take you just through two. This is Claude Shannon, the man in the 1950s and 60s who developed most of information theory almost by himself. This is the classic Venn diagram, which shows the overlapping of uncertainties. So the two ovals you see, the red and the blue, are representing the uncertainty associated with random variables. X is blue, uncertainty of Y is red on the right. This just represents the total number of different states that the variables might take on and their relative probability distributions. So it's the complexity, the amount of randomness in a random variable that's measured by these entropy measures, and to the extent that one random variable has something to say about another random variable, which is what Joseph Kittler's classical work was largely addressing, that is the intersection between these two uncertainties. So pattern recognition as the overlap of uncertainties. In the channel context, the left index is how much crescent shape, this portion just here, the crescent, oops, oh, I'm sorry, it's a bit dangerous to use that pointer. So we have, well, anyway, these uncertainties could be related to the channel concept as input and output, and to the degree that the channel is a reliable channel, there should be no uncertainty about what the output is given the input, and likewise there should be no uncertainty about what the input was given the message that you received, and so then the intersection should be complete and they should be coextensive. But there are other ways to apply information theory to biometrics as well as that. For example, we might, in that case we looked at the X and Y as input identities and output or inferred identities, but we could also take the view that the input to the channel is an identity of a person, X, but the output is simply the patterns themselves that are received. What signals, what biometric patterns does this person emit? And there will be some uncertainty about what you get as a biometric given an identity. And similarly, the crescent-shaped region on the right is the other conditional entropy, namely, given an identity of the person presenting, how much uncertainty remains about the biometric patterns that the person may generate. So you can see there are various ways in which information theory is very germane to understanding biometrics. In particular, in this interpretation, you can see how those two conditional entropies speak about the false match probability and the false non-match probability, or the failure to match, false accept, false reject. Now, entropy, my kind of starting thesis is that the entropy of biometric patterns, first of all, is something we can calculate and that we should speak about and think about quantitatively. And I claim that it is really the origin of their collision avoidance. In other words, the resistance to false matches that is possible biometrically with biometric patterns is a reflection of their entropy. The more entropy, then the more unique each pattern is. The analogy is the idea is very analogous to the strength of a cryptographic key is related to the key length in bits. The key length in bits of a cryptographic key determines its entropy. It is exactly the key length in bits if there are no correlations, and that entropy determines the hardness of the key. So people want to have a longer key for stronger encryption. These are just 4 pictures of actual iris codes. Maybe you can get even just a visual impression of the fact that they have a lot of entropy. There are a lot of bits and they look pretty random. We will focus on the predictabilities that nonetheless exist inside iris codes, the correlations of different kinds that exist inside iris codes, and we will calculate the channel capacity of iris recognition as a reduction from how much the entropy is reduced from the number of bits. Okay, so to summarize this kind of overall review, the randomness of biometric patterns is summarized by their entropy. The greater the number of possible patterns, the greater the entropy. The more uniform the distribution of patterns, the greater the entropy. Any internal correlations or predictions reduce the entropy of patterns. If something becomes predictable, you've lost uncertainty, you've lost entropy. Quantitatively, you can estimate an lower bound. The entropy h in bits means that there are at least 2 to the power h different possible patterns. That's the lower bound, because if these occur with non-uniform probabilities, then that same entropy can mean more than 2 to the power h number of patterns. This is the classical Shannon source coding theorem about how the source statistics determines the entropy. Okay, and in general, greater biometric entropy means that accidental false matches or collisions are less likely, just like for the length of the key determining its hardness. And so if you want to ask the question, for example, over what size of population can a given biometric technology work and still have collision avoidance, avoid accidental false matches, you have to think about the entropy of the technology. Okay, so another sort of classical idea from biometrics is about the within-class variability relative to the between-class variability. Here we have just two distributions. They happen to be Gaussians with equal variance. Obviously, that's normally not the case, but they have some overlap and a decision criterion that you move, a threshold, a match similarity or dissimilarity threshold that you move around. And the overlap, that the errors, the portion of either distribution that lies to the other side of the decision criterion is the error rate, the false match rate, or the failure to match rate. And of course, you want them not to overlap, either by pushing them apart or making the two distributions narrower. That's the art of designing a feature extraction algorithm or choosing a feature set. And what matters is to minimize the overlap, subject to cost benefits analysis. The two different types of errors may have different costs, so you don't necessarily put the decision criterion at the crossover point, but the key thing that matters is the magnitudes or the relative magnitudes of within-person variability and between-person variability. Now let's just begin with looking at that question quickly with some examples from FACE, which is a low entropy biometric, and we have a classic problem. Both of those distributions are badly affected by the fact that in face recognition you have low biometric entropy. So I'll show you several slides with the same title about low biometric entropy. In this case, we deal just with twins. All these are pairs of twins. They're different people, but they look indistinguishable, I think, from their twin. And of course, so the between class variability is much, much smaller than ideal, and in fact it's smaller than the between class variability for different people who are not twins. These are monozygotic twins. You know, about 1 pregnancy in 80 produces twins. 1/3 of those are monozygotic or identical twins, 2/3 are dizygotic. So you could say that 1 pregnancy in 240 produces a pair of identical twins, which means that 1 person in 120 has an identical twin overall in the population. So about 1%, which in a sense means that the minimum false match rate for face recognition is at least 1% in the population, if it's true that face recognition cannot distinguish monozygotic twins. Maybe that's not always going to be true. But this is the case of people sharing 100% of their genes. However, the genetic penetrance for facial structure continues on down to people who share 50% of their genes, like full siblings or parents and children or double cousins, also can look indistinguishable from each other apart from age cues. And finally, even people who are completely unrelated to each other can look almost indistinguishable from each other. These are what we call Doppelgängers, from the wonderful German word, a double goer, double walker. There's sort of a little cottage industry to go around finding people in London who are completely unrelated to each other but who look indistinguishable. So we have this problem of low entropy with face recognition. And of course, we also have the problems of changes with time and other factors. This is just the aging problem with faces over this famous British politician after 35 years. The problem of pose variation, fixed expression, age, and illuminance. The problem is that in all these cases you see that the same person looks much less like themselves over time or changes in illumination pose, then they may look like other people. So those distributions have the wrong overlap. And finally, we have what I call celebrity culture biometrics. Celebrity culture biometrics in which everything can change through surgical interventions. This sad story of Michael Jackson, who he started off life as a very handsome kid, handsome teenager, but after repeated surgical changes to his nose and his chin and to his gender, apparently, and his race, I don't know what we're looking at here at the end. So celebrity culture biometrics creates a new set of problems of failures to match. Okay, now I want to talk about epigenetics and phenotypic and genotypic traits. An interesting thing about face recognition is that the facial phenotype always changes over time with age, but remarkably, monozygotic twins track each other. They track each other over time. They look like each other at all different times in generally across their lifespan, which leads to this paradoxical, sort of philosophically interesting situation that monozygotic twins at any given point in time look more like each other than they look like themselves at either earlier or later points in their lifespan. Okay, well, now let's talk about the birthday problem. This is an analogy I'll use for understanding population size potentials with biometrics. You have probably all, if you've taught a course in probability, I'm sure you're familiar with the classical birthday problem. It simply asks this: how many people must be assembled, chosen randomly, before it becomes more likely than not that at least two of them share the same birthday? Any ideas? Any rough calculation? It takes a little bit of work to do the calculation. The answer is 26. As soon as you have 26 people together, it's more likely than not that at least two of them share the same birthday. The reason is not difficult. There are n times n minus 1 over 2 different pairings of people. When you have n people assembled, the probability of any given random pair sharing a birthday is 1 in 365. So 1 minus that is the probability of not sharing. You must raise that to the power of the number of people, the number of pairings, and ask when is that number less than 0.5. And it's easy to show that happens when you have just 26 people in a room. At least two of them will share the same birthday, in all likelihood. Now, using that idea, I want to talk about the biometric birthday problem, which is about a different kind of collision. How many people n must be assembled, again, chosen randomly, before it becomes more likely than not that at least two of them will have a biometric collision, a false match, using a biometric modality which has some specified false match rate. So what used to be 1 in 365 now is a variable FMR, whatever the false match rate is, 1 in 1,000, whatever. How many people must be assembled before it becomes more likely than not that you will have a false match, a collision biometrically among that group? Here's the answer. It's not difficult to derive this expression. The number is related inversely to the square root of the false match probability, and the derivation is again the same derivation as before, assuming that the false match rate is something small, like less than 1% or 1 in 1,000, whatever. this condition here will be satisfied once n is greater than or equal to that number. So let's just take one example. I said earlier that face recognition probably has a minimum false match rate of 1%, if only because of the birth rate of identical twins, but that's an optimistic estimate. Even I think that some benchmarks on mugshot database, some benchmark tests using mugshot databases tries to measure it at a false match rate of 1 in 1,000. The classical NIST test was for high quality images, assuming the false match rate is 1 in 1,000. Well, in that case, the size of the group that will give a false collision for face recognition is just 38. As soon as you have just 38 people together, you'll get collisions, doppelgängers in the group. So please let me invite you, if you're flying back on your airplane, the next time you're at an airport, if you're standing in a queue at passport control, please just turn around to look at the first 38 people behind you and try to spot the doppelgängers. It's an interesting exercise. This is a problem, this fundamental problem is what I call the elephant in the room. Do you know this is an English expression? Elephant in the room, it means the problem that nobody's quite ready to acknowledge and talk about. If you have small biometric entropy, this is the elephant in the room. Here, I have an actual picture of an elephant, in the boardroom. And we'll return to the zoological theme a bit later, just like the first slide tried to introduce. Okay, here actually we have a group of 40 randomly chosen meditators. Well, they're not random, they're all meditators. I think they're mostly women, but among these 40 meditators, can you spot a pair of doppelgängers? This is to prepare you for the test at the airport. Didier, the forensic expert, Didier has already found one. Well, I think, is that one of yours, Didier? I think this woman is a doppelganger with this woman. But who knows, it's low resolution, it's maybe not a fair test, but you see my point about the doppelganger rate. Now this raises a really fundamental question about when you can do identification with biometrics rather than mere one-to-one verification. I feel that there has generally been an underappreciation of how astronomically more demanding is identification in sizes that are non-trivial than mere verification. I mean, if you only want to do one-to-one verification, I think you may as well measure the length of somebody's toe and the big foot. That's probably good enough. But if you want to do identification on a database of any significant size, 38 or whatever, you really need to think about entropy. Okay, well now, of course, I'm going to move on to the iris as an identifier. It's a highly protected internal organ of the eye, which is externally visible from a distance of up to some meters. The most ambitious, successful iris at a distance systems that I've seen work at 3 meters. People talk about 50 meters. I don't believe that. You need a telescope and a dead person that's not moving at all to even try to do it at such great distances. But we have this random pattern of great complexity and uniqueness, and it's epigenetic. It's not genetically determined apart from color, and it's apparently stable apart from pigmentation changes. There's no evidence for any visible changes in iris patterns over time, although there are some strange claims about biometric templates aging, even though you cannot see any changes in the iris pattern itself. I would begin with some visible images of irises in the visible wavelength. You see this very rich, random interwoven texture called the trabecular meshwork. It's harder to see in a very dark-eyed person, so that's one reason for using infrared light, near-infrared light. But if you, again, just visually, I hope you get some impression about how much entropy, like a plate of spaghetti of sticky noodles that sort of randomly is thrown down on a plate, you know that you're going to get a lot of entropy there. A very beautiful pattern. On the other hand, from the standpoint of human forensic possibilities, these features don't even have names. How would you possibly train a human forensic examiner to make a decision about a matching decision when you can't even put a little circle around the feature like the minutiae of fingerprints, a ridge ending or a branch point or a sweat pore? What is a feature here? It's a multi-scale concept, another key idea from information theory, that information is distributed across multiple scales of analysis with different information contained in different frequency bands. Another key concept from Shannon's third theorem, that why the bandwidth, frequency bandwidth available determines the information capacity of a channel. Multiple scales of structure means multiple bands of frequencies. These are really rich connections and important ideas. Of course, even dark brown eyes show rich texture when you capture eyes in infrared light, and they are epigenetic. Every biometric, in fact, lies somewhere on a continuum between being genetically determined, meaning genotypic, or not, so epigenetic outside of genetic control. In this, the word has other meanings, but here it means outside of genetic control. Examples of genetic traits include, of course, DNA, race, gender, and so forth. Epigenetic traits includes fingerprints, although Anil Jain, I think, has shown some small correlations in class types among identical twins, and iris patterns are epigenetic apart from eye color. And of course, in the middle of this continuum, we have facial appearance, because identical twins look identical, but they change over time, so it's a phenotypically change. The phenotype changes, but they track each other, so it's a very interesting sort of mixed case. These are just some examples of monozygotic twins. You can even tell from the facial structure that they're twins. At the age of 6, we've computed the distributions of Hamming distances for iris patterns for identical twins, or for that matter, the right-left patterns of one person's eyes, which are also genetically identical, obviously, and they have the same distribution as for unrelated people. And here are some 18-year-old girls, the same story, and 78-year-old men. They look very different from, their faces look very different from they were as children, but still the same story. Overall, because of these huge differences in entropy, some NIST comparisons about face versus iris recognition confirm that there's a factor of 100,000 difference in their accuracy. They differed by a factor of 100,000 to 1 in the false match rate. This is just taken from a NIST report, and also a 10 to 1. They also favored iris recognition by a factor of 10 in miss rate. So 10 times better miss rate, 100 times better or lower false match rate comparing iris and face. That's already a picture for why entropy matters. Now, iris image acquisition has not always been very user-friendly or not as easy as it might have been. In fact, this is my favorite, my metaphor for what iris image acquisition was like may have felt like for some of the early image acquisition systems. But of course, today we have a standoff distance of about 2 meters and a much better capture volume, and people can even be walking at 1 meter per second. So please don't take the image on the right as the definitive version of the iris recognition image acquisition process. It's a nice picture, though. Okay, so briefly, how the recognition iris algorithms work. I won't take much time to discuss this. It's not my main focus, but I should review it a bit. Of course, you have to do segmentation at first, localizing all the inner and outer boundaries and the eyelids, excluding eyelashes, scrubbing of specular reflections, and then fitting the precise boundaries with active contours, which must be very flexible. Not just, you cannot assume that they're ellipses or other simple forms. And then we have to map the iris texture between those boundaries into dimensionless coordinates so that it's scale invariant and position invariant, and indeed, ideally, pupil dilation invariant, although that's limited. And then encode a compact wavelet phase-based description, which is suitable for a database search and matching using very fast logical operators and similarity metrics. A simple logical implementation of a test of statistical independence that works incredibly quickly, millions of iris codes per second. This is just a quick summary of finding the boundaries of the inner and outer boundaries of the iris and the eyelids. This is an actual trace showing how non-circular, non-annular the actual iris boundaries typically are. The blue curves show the actual shapes of iris boundaries, and the dotted red dash is what the circular model would be. You can see it's quite, a circular or annular model is quite inaccurate. I use a Fourier series expansion to extract the shape of the contour. Essentially, the blue curve can be expanded as a Fourier series using any number of terms, depending on the quality of the match you want and how much flexibility. Basically, in computer vision, I think a general rule is if the data is strong, you should use weak models. If the data is weak, you should use strong models. So, well, good quality data can support complex models. Low quality data should only be used to support simple models. So I use 4 Fourier components to give a flexible description of the outer boundary, the limbus, and 16 Fourier components to give a more precise expansion for the inner boundary. And here you see some examples of clearly non-round inner and outer boundaries. The two snakes in the snake boxes here are the curvature maps for the outer and inner boundaries. The outer one, the thick snake, is thick because the outer boundary is soft. So it's as a function of radius. It's the strength of the edge gradient evidence as a function of radius inside the snake box. So the radius is changing up and down as a curvature map. And you can see that the Fourier series is the dotted curve in the center. So I'm talking about this shape here. That's the Fourier boundary expansion for the outer curve, which of course is interrupted here and here by the eyelid, whereas the thin snake down here is thin because the inner boundary is a much sharper boundary. It's a true black hole. But also it's non-circular. So I think my recommendation is Fourier boundary descriptors for the mapping and segmentation of the boundaries. But of course there are other methods that many people have explored. Many people whose faces I recognize here in this room have worked on alternative active contours. Another example here of a very non-circular pupil, etc. It's easy to find these, and it's very important to adapt to use these kinds of models in segmentation, because if you miss-segment, you take a big hit in the false reject rate, failure to match rate. So this is an important step of the whole process. You've probably heard the old saying, you can't fit a round peg into a square hole, or you can't fit a square peg into a round hole. I forgot, well, probably they're isomorphic. This is, of course, just not a real pupil, it's a Photoshop one, but guess what? You can even do the Fourier boundary series expansion for a square-shaped pupil. So this is a Fourier series mapping the curvature map to fit the square pupil. It's just a bit of a joke. Okay, so how do we set the bits? Well, you probably are familiar with the use of complex value 2D Gabor wavelets, which I'm not getting this right animation. It'll do. These are setting the bits a bit like a DNA sequence. There are 4 states. Instead of 4 base pairs, we have 4 phase values. The complex plane is divided into 4 quadrants. You could use more phase resolution or less, but anyway, the bits are set based on whether the phasor, which is the projection of a given patch of the iris onto these Gabor wavelets, because they're complex, that projection is a complex number. Complex number lives somewhere in the complex plane. You can divide the plane into 4 quadrants. If it lives to the right or left of the imaginary axis, that is how we set the real bit. This H sub RE is the real bit. It's 1 or 0, depending on this being greater than or less than 0. And also there's an imaginary bit, which is depending on whether the second 2 projections are above or below the real axis. So I ask you to think about imaginary bits or complex valued bits as well as Boolean bits. Why shouldn't we have complex valued bits? We just need a new name for them. I don't know, Plix, something like that. So we have complex valued bits, and the iris code is made up of them. It generates a phase sequence of the iris pattern that is meant to be dimensionless and invariant to changes in size, position, and dilation. The bits, the statistics are very important here now. The bits in iris codes are equally likely to be 1 or 0. This makes them maximum entropy codes in a bitwise sense. If different irises had some common structure, this distribution would not be uniform. It would go up and down. But when bits from different iris codes are compared from different eyes, those comparisons are Bernoulli trials. Now this is one of the key things that makes iris recognition so fast, so parallelizable, and so scalable, because you can do all the exclusive OR to detect disagreement in bits. You just need to run an exclusive OR operation on as many bits at the same time as the word length of the machine. You can take 2 64-bit integers on a 64-bit laptop, and in a single machine instruction, so a few ticks of the clock, compute the exclusive OR, generate a third 64-bit integer, each of whose bits is the XOR of the first 2. In other words, it'll detect when the 2 bits disagree. So that's 64 bits at once at 3 gigahertz or 1 gigahertz. That's why it's incredibly fast. That's why UIDAI can do trillions of iris code comparisons every day in India. That's their workflow. Trillions every day. In fact, it's about 100 trillion every day. We'll come to that a bit later. And that it's a very rapid way to do the matching. And indeed, in terms of programming, it's this simple. You see this one line of pseudocode? That's it. That is the matcher. This one line is taking 2 64, or in this case 32-bit integers, taking the XOR between A and B, masking them with 2 noise masks that exclude eyelids and eyelashes and noisy parts of the iris. So it's the XOR of 2 words ANDed with two other words, which are their noise bits, and that you get the new result immediately, and that's 64 bits worth, so it goes through at a very blistering speed. Iris code bit comparisons can be regarded as correlated Bernoulli trials. We'll focus on the correlations in a moment. The main point is that because it's like coin tossing. Comparing two bits from two iris codes is like tossing a coin. They have a 50-50 chance of agreeing or disagreeing. The important issue is that there's memory. They're correlated in successive tosses, so it's a correlated Bernoulli process. But the fundamental class of distributions you get from Bernoulli trials is the binomial distribution. And the point is that you have these huge factorial terms. You know, each of these factorials is n might be 250 factorial divided by half of that. So the big factorial terms mean that you get very, very rapid attenuation of the tails. That's the key reason why iris recognition has such a famous resistance to false matches. The tails of this distribution decay from the peak very, very, very rapidly. Sorry, I should be careful not to do that. Okay, I'll put it away. That's the reason for the very rapid attenuation of tails. That means that very, very tiny, if you move down the, I can use this pointer. If you look at it doesn't show up on the screen. Okay. On the first column, you see the fraction of the Hamming distance, the percentage of bits that are allowed to disagree in this distribution. Well, never mind. The fraction of bits that disagree that's the horizontal axis, the x-axis of that histogram. So if all the bits agree, that's on the left corner, 0. If all the bits disagree, then that's 100%, that's 1 on the right side. Here we see the fraction of bits that are allowed to disagree. And many years ago, from smaller databases, I published some predictions about the predicted false match rate for each of these decision thresholds that you might choose. And then years later, using new databases, which did not even exist at the time of my published predictions, NIST did a really big test, in fact 2 different tests, really confirming quite to a remarkable degree those false match rates as a function of the fraction of bits that disagree. Their first database used more than 1 billion iris comparisons. The second used more than 1 trillion iris comparisons. How did they do that? They took 2 databases, each of size about 1 million people, which were from geographically completely overlapping, completely distinct places. One was American college students, and the other was in Afghanistan and Iraq, a field deployment by the military. It was assumed that there were no overlap in those 2 populations. So 1 million times 1 million gives you a trillion, 10 to the power 12, cross comparisons, 1.2 trillion, which makes it possible to extend this table down as far as the bottom row here at a Hamming distance of 0.28. I had predicted that the false match rate would be 1 in 90 billion, which is a number you can support when you have more than 1 trillion, more than 10 times more comparisons. You can speak about a measurement of 1 in 40 billion when there are more than 1 trillion comparisons. And that's not bad, it's a factor of 2. If you go up to 0.3, in fact, the NIST conclusion was a factor of 2 better in the other direction than my prediction. So I believe we have a solid and independently tested basis for the legendary false match rates associated with iris recognition. Okay, now I want to talk about the universality of the iris code distribution. This is 100 billion iris comparisons. This comes from the UAE, a large Middle Eastern database, which includes people of 152 nationalities. It was we have about 2/3 of a million enrolled iris codes. If you do all the different cross comparisons, you get 200 billion. We divide it into 2 half lists, in which each individual eye was compared against all the other eyes in the other list, which means that we can generate 315,000 distributions of impostor scores. So we're talking about entire distributions of impostor scores, hundreds of thousands of entire distributions of impostor scores. And I want to show you the statistics of those distributions. This is the universal distribution. It's not centered on 0.5 anymore because we have to allow different rotations, scroll the iris codes and choose the best match. So that's sampling, extreme value sampling, finding the smallest value after all the rotations. So it's shifted to the left. And now, the important point I would like you to observe is that between all the bits agreeing, that's 0, and all the bits disagreeing, that's 1, 99% of all comparisons between different eyes fall in this narrow range of between 40% and 50% of the bits disagreeing. Is that a narrow range? Well, how long is a piece of string? I think it's a narrow range. So that's an important point. It means that all different eyes are roughly equidistant from each other to the extent that for this narrow boundary between 40% and 50% is considered to be a narrow portion of the total possible range. So that's quite a strong statement that for this biometric, that all different eyes are roughly equidistant from each other. Moreover, we have what's a nearly universal impostor distribution. What is shown here are histograms of the means, that's the blue, and the standard deviations, that's the red, of all these 316,000 different distributions of impostor scores. Okay? So we've extracted those two statistics from each of the 300,000 distributions and plotted their distribution. And I say these are remarkably narrow spikes. That's quite a narrow range of means, quite a narrow range of standard deviations among these 300,000. So to the extent that we regard these two distributions as extremely narrow, that means that there is a kind of universal impostors distribution for iris codes. Well, how universal is it? Among those 316,000 different impostor distributions, we did a quantile series to order them either by their means or to order them by their standard deviations. And then from the ordering, you can generate quantiles, like what's the most extreme cases, or the bottom 1%, bottom 5%. So what you see here are, the black is the canonical distribution from the entire set that I showed you. The colored curves are the 20 cases with the largest false match rates. These are the largest false match rates out of the 316,000 distributions. And you can see it's a bit shifted to the left. And similarly, if we take the 20 most extreme, the smallest false match rates among the 316,000 distributions, you get the colored distributions that are shifted a bit to the right. Well, there's an interesting tradition in the subject of biometrics called Doddington's Zoo, which began originally with speaking about wolves and lambs and goats. And then that was expanded by Jaeger and Dunstone to speak of other animals, chameleons, doves, phantoms, and worms, depending on how both of the distributions deviate from the standard case. So the dotted black curves are just some abstraction of the standard biometric situation for any modality. Chameleons are those in which both distributions have shifted to the left, so they're more similar to each other. People, both whether they're same or different, they all look a bit more alike, similar to chameleons. On the other hand, there are phantoms. Phantoms, as you know, shift to the right. They're protean, so hard to say what they look like. Doves are those, that's the desirable case. Doves are nice. The two distributions move in opposite directions, which means less overlap. And then the worst case are the worms, because the worms are very unpleasant, and the two distributions have moved closer to each other, and so there's more overlap. Well, we now need a new zoological name to add to Doddington Zoo for those rare creatures that are exceptionally unique, shifted to the right. We don't know what their authentics distributions are like because there's no data from that particular Middle Eastern database to allow same person comparisons. But given merely the observation that these impostors distributions are unusually different from each other, do you have any ideas about a name for? I would like to ask you, help me provide some ideas about a name for those creatures. Well, perhaps you've read the title of the. Sorry.
Black flamingos.
Okay. Well, I propose this taxonomic solution to the mystery. We have. Creatures or people whose because biometric entropy is the origin of uniqueness, and higher or large entropy pushes the distribution of Hamming distance scores closer to 0.5. The combination of entropy and uniqueness gives us the new name, Entropod unicorns. Now, this is a rare picture. These are very rare creatures, and so it's hard. This is an actual picture of an actual Entropod unicorn. And you rarely encounter these pictures. Okay, so there you have this addition to Doddington Zoo based on the higher entropy, which produces higher uniqueness. Now, we need to zoom in a little bit more. I'm running low on time, so I'll go through this quickly. we have to remove any score normalization from that analysis, because score normalization compensates for the fact that more bits or fewer bits may be available for comparison because the eyelids may be open or closed. So detecting eyelids and indeed eyelashes requires score normalization. We want to remove that from the matching situation by only dealing with the case in which the number of bits available is from a very, very narrow window, from 906 to 916, which is the typical case. And that narrows down the combination of 100 billion comparisons to just 4 billion in that narrow window, and now we can speak of do the same analysis without any score normalization as a potential confounding factor. Here are the distributions of means and standard deviations for the surviving 250,000 distributions. So these are 250,000 impostors distributions, each one made by comparing one eye with all the others, harvesting just those in which that number of bits was comparison and was available. And again, you see a very narrow range of means and a very narrow range of standard deviations. Now, why is it beneficial to have a universal impostors distribution? First of all, these are important points about the operational deployment of biometrics. If you have a universal distribution, then a dissimilarity score threshold can be immediately translated into a false match probability and a decision confidence level. You can't do that if you don't know or believe that you have a universal impostors distribution. Secondly, it allows a straightforward extrapolation from a single comparison false match probability, given some score, to the net error probability if that score was observed only after searching a large database. From extreme value sampling, if you look for the smallest value or the best score, the highest whatever, after 1,000 or 10,000 searches, you'll get more and more extreme results. So to calculate the result of the meaning of a given score, you have to take into account how many comparisons were made before you found that as the best match. You can't do that unless you have a universal impostors distribution. Also, the number of alternative comparisons that were made before a given best match was encountered can be factored into the interpretation of the observed score. This is relevant to the one-to-first and one-to-many matching modalities. And finally, I say, if a biometric modality cannot assume a universal impostors distribution, then any observed similarity score must be further qualified by whether the subject is the type of person who has many doppelgängers or few. Okay, now continuing this Quantile series for these distributions without any score normalization, we did the Quantile series, first of all, on the means, and you see two outline curves, the red and the blue. Those are the most extreme, highest and lowest false match rates among all the 250,000 distributions. It's a pretty tight cluster, but these are the two extremes, the most extreme, and doing the same Quantile series on standard deviations. Here again, you see a different red and blue curves for the most extreme. So obviously the red curve will have the highest false match rate, the blue curve the lowest false match rate, but those are the two extreme distributions among the 250,000 distributions, which are summarized as the black curve around which all the others cluster. And this is based on a quantile analysis, so we find the order, we'd make an ordering of all the distributions. And now we have to zoom in even more closely because that did not reveal much dispersion. Here is a quantile series that looks at the first 2.5%, the lowest 2.5% of the means, and the highest 2.5% of the means. Those are all the colored curves that you see relative to the black curve in the center, which is the canonical case. So you can see there is these are the limits of universality. I'm trying to show you the limits to the universality of the impostors distribution. There is some dispersion if you look at 250,000 distributions. And likewise for standard deviations, we see a similar picture when the Quantile series involves an ordering on standard deviations. Those two are correlated with each other. This heat plot shows that there's a tendency for higher standard deviations to be associated with lower means and vice versa among those 250,000 distributions. And this is an interesting structure that, of course, has never been observed before or discussed before. Finally, we can interpret all of that in terms of the impact on false match rates. This is, again, using the Quantile series, so where you are in the distribution of means on the top among the 250,000 distributions, and where you are in the distribution of standard deviations for the same set, ordering them into quantiles, for which cases is there some reduction in false match rate, that's green, and some increase in false match rate, that's red. And you see that our Entropod unicorns have once again entered the picture. The region on the right for the Quantile series of means, those are the Entropod unicorns. It's another rare picture of them. And likewise for standard deviations, these ones on the left are the Entropod unicorns with unusually unique iris codes. Okay, now I want to leave you with the recipe for calculating biometric entropy for any modality. You must first encode a large database of biometric samples using the appropriate resolution, and I have to tell you now that the results will depend on the sample, on the resolution of your samples. It's not surprising if you take an ever more microscopic view of the iris, for example, you'll find structure and details at ever finer scales, and that will increase the apparent entropy. So these calculations are dependent on the resolution that you choose for the samples. Then you generate the all against all impostors distributions, like those 100 billion that I showed you, and construct then a multi-scale Markov process that emulates correctly the sample statistics and impostors distributions. So that would be a Markov chain that looks a bit like this, for example. You have, in this case, two states. HMMs are, of course, very standard ways to model all sorts of phenomena in speech recognition and gesture. Any articulated behavior is usually modeled now as a Markov chain. The two black disks are the two states. In each state, different things happen with different probabilities. Here, if it's a language model, then you emit letters. Letters are emitted with different probabilities in the different states. Of course, this may be a much longer chain. So you have some probability structure associated with states, and you generally don't know exactly what state the system is in. Okay, well, once you have a Markov process model for your biometric data, which generates all the statistics that you care about, so whether it's run length sequences or match probabilities, whatever you think are the important statistics for your modality, having constructed a Markov chain that generates that, and I'll show you many examples, I hope, if there's time, of actual such processes, Markov processes generating not only iris codes, but generating actual iris images. Having got the Markov process, you can then calculate the entropy for each state. The classical Shannon definition of the entropy of a random variable is this first equation here, based on the probabilities of the things that happen in that state. But then you also have to calculate the overall state occupancy probabilities from the flow equations. For a Markov process, the way the flow rates tell you how much of the time is spent in each of the states, and so you can calculate the probability of occupancy of each of the states, as well as calculating the entropy associated with each state. And then you just, so we have these two terms, two numbers that we just multiply together. The overall, this is the definition of the overall entropy of a Markov process. It's the linear combination of the entropy of each state weighted by the occupancy probability for that state. And that can be expressed as a bit rate. We can calculate the entropy as bits per bit emitted rather than bits for the entire pattern if we prefer. Okay, now let's apply this to this is an actual iris image. In fact, this is actually, it's a low quality picture because it's from my original patent 20 years ago, 25 years ago. The upper trace is just an actual trajectory around the iris, the grayscale value from a particular circle going around the iris. Raw data, the second trace is the output of the Gabor wavelets. It's essentially a convolution, so this amounts to a bandpass filtering. The bandpass filtering output in the second trace is quantized by asking is it greater or less than 0, the real part and the imaginary. Quantizing by zero crossings gives you the bit sequence at the bottom, right? You can see how that corresponds to whether the second trace is above or below 0, and that is an iris code. So there you have a bit stream for an actual iris code. And the important point is that there are correlations. The run lengths of these bits are not pure binomial. They're not just simple classic independent uncorrelated Bernoulli process. There are correlations and longer range oscillations. Now, local correlations are because of the low pass character of the filter, the wavelets, but because they also are band pass, they have a high pass element. That very importantly introduces correlations in phase. And many people are not aware that you get correlations in phase or oscillatory behavior that persists for a period of time inversely proportional to the bandwidth, just like you get local correlations of amplitude. So we have to think about both the high pass and low pass aspects of a bandpass encoder. Now, it's of course obvious that iris codes have high entropy compared to other biometrics. That's what gives them their collision avoidance, but we have to now analyze the consequences of projecting the iris patterns onto Gabor wavelets, which is a kind of bandpass filtering. So why is the entropy of iris codes less than 1 bit per bit? It's classically known that if you low-pass encode a signal, you get local correlations in amplitude. That's like blurring. If you blur an image, neighboring pixels are similar to each other. They change very slowly. It's less well known that bandpass introduces correlations in phase, as I mentioned. And in both cases, the persistence of both types of correlations is inversely proportional to the encoding bandwidth. So low-pass filtering gives you a correlation amplitude that lasts for a reciprocally long period of time. The more low-pass, the longer the correlations last. Likewise, the narrower the band-pass filter, the longer the phase correlations last. In the limit where only one frequency is allowed through the filter, you get a pure sine wave that is in phase forever and ever. So you see in that extreme case, the reciprocal nature. Now, in the Gabor wavelets have bandwidth about 1.5 octaves. How much do they limit the capacity of the iris code? Well, here you see the actual phase coherence within iris codes. This is a plot of how the Hamming distance between iris codes varies as you move, with a relative shift in the position of a given iris code. Take a given iris code, move it back and forth. How much does it predict itself? And you can see it's not a flat line. Hamming distance may go up and down with scroll distance. Andreas Ulm is here. Andreas and his group actually, I think, were among the first to observe this kind of phase coherence. Also Jim Matey as well, by moving iris codes around. So that is already a form of internal prediction, which is one reason why entropy is reduced. Now, a Markov process model for iris code bit streams, and indeed also iris images, is a sticky oscillator. It looks like this. It's a two-state Markov process. In state 0, bit 0 is emitted with probability alpha, but with probability 1 minus alpha it emits the other bit and then moves to the other state. The same thing happens in the other state. Probability alpha continues to emit 1s, but with probability 1 minus alpha, it oscillates back to the first state. Now this is a sticky oscillator because if alpha becomes very large, it will almost never leave whatever state it's in. If alpha goes to 1, it will never leave that state. So it just produces a long string of 1s or a long string of 0s, no changes. On the other hand, if alpha becomes very, very small, it switches states on almost every bit, and then you get an alternating bit sequence, which again is completely predictable. Those two cases are symmetrical in their loss of entropy, and indeed the Shannon equation for entropy as a function of probability gives complete symmetry as a function of alpha's deviation from 0.5. Very important concept. And if you actually, you can generate the distribution of iris codes using this Markov process. The top is an actual human distribution, again without rotation, so it's centered at 0.5. And the bottom one is just that two-state Markov process generating exactly the same run length statistics and the same distribution of impostor scores when you choose the Markov parameter to be 0.9. However, that's just matching a biological trait. That doesn't tell us the channel capacity of the iris code, which depends on in which the anatomical correlations are no longer a source of correlations in the bit stream. So my last question is, what's the channel capacity of the iris code? This requires a white noise analysis. We generated 500 synthetic white noise images. You see an example here. Here's another one. You can see just the variation in the pixels. They're Gaussian samples from so the histogram in the lower right is just the distribution of pixel values from 0 to 255. So a flat power spectrum means you have Gaussian sample pixels. This is the way to test in information theory the capacity of a noisy channel, and generating all 125,000 cross comparisons among these white noise iris codes gave the distribution on the top right. It's narrower than the human distribution. And if you want to model the white noise iris code distribution using the Markov process, you can do it, but you need a different Markov parameter because it's a more oscillatory. The bits change a bit more often, and so 0.867. Here is the same kind of sequence, a set of traces for the white noise signal sample that's on the top, and then the middle trace it's the output from the Gabor wavelets and the bit stream in the bottom. Please compare the top trace of this white noise iris image with this actual sample from a real iris image. You can see the difference between the white noise source and the top trace for an actual iris, because there are anatomical correlations within a given iris. However, the output of the Gabor wavelets, the second trace, is not all that different. It's a passband, so you're getting the same passband out, and the bottom are the bit streams. And from the entropy of the two-state Markov process, we can now calculate the channel capacity. The conclusions from the channel capacity analysis are that white noise iris images reveal the capacity of the iris code and how much is used, how much of the channel capacity is used by the actual iris anatomy. The bandpass characteristic gives us a sticky two-state Markov process. Numbers, finally, the intrinsic capacity of an iris code from the white noise image analysis is, I say, about 0.566 bits of entropy per bit encoded. Natural irises, on the other hand, encode less than that, about 0.469 bits of entropy per bit encoded in the iris code. And the difference between those two bit rates, or I should say entropy, the difference between those two entropy rates estimates the anatomically missing randomness in irises within the spatial frequency passband encoded. Finally, my last intended slide is a sort of critique, a sort of statement of some limitations and critique of biometric entropy. First of all, the estimates that you make will depend on the resolution of samples. Second, the estimates will depend on the biometric algorithm. Third, the calculations depend on building a Markov model. And the biometric entropy, but what you get, of course, the biometric entropy determines the achievable false match rates, and therefore the potential population sizes for collision avoidance over how big a population can you use this biometric. But of course, false match rate isn't all that matters. You care about false non-match rate, and that limits the resolution that you wish to deploy. And in one-to-one verification scenarios, all of these criteria about population sizes and false match collision avoidance are much less important. Finally, this slide shows the application of these same ideas to generate synthetic databases of iris images used by fitting the parameters of the Markov model you can see the sequence. The Gabor wavelets are just reintroduced, resynthesized, recombined to make synthetic iris images that you see in the lower right corner. That's just a linear combination of the Gabor wavelets whose phase is set by the bits of an iris code that comes out of the Markov process. The Markov process gives us bits. The bits tell us the phase, or the plus and minus amplitude. The Gabor wavelets, add them all together, get an iris image, build a database from them, compute their Hamming distance distribution, and then tune the parameter of the Markov process if you want to fit if you wish to match the biological case. And I leave you with that. I have other slides about the applications of iris recognition now in vaccination retrieval programs, a pilot study that will begin to retrieve vaccination records in countries, in developing countries in which there are no reliable records. And I can tell you a bit about that, something with the Bill Gates Foundation and other applications as well. But I think I've been speaking for an hour, almost an hour, and I should invite the chair to allow somebody else to have a go. And if there are questions or interests, I'll return to those other slides.
Thank you very much.
I think I can speak up. So for sure, the true irises are not generated by wavelets. So what is generating the different patterns of the iris?
You can, in fact, exactly generate iris patterns from combinations of Gabor wavelets. I have a slide I could show you. In fact, they are a complete basis. So these same Gabor wavelets, if you use a code book that contains many different sizes and frequencies, you can make an exact reproduction of any given iris, and I've done that, and I can show you some slides. However, we want to use a more restricted code book, which corresponds simply to the wavelets that are used in the iris code. So you want to have something for everybody. What I mean, something for everybody, some irises have fine structure, some have coarse structure, so there's a library of code book wavelets that tries to offer something for everybody. This looks impoverished because it's only using 2 frequencies, but the answer, well, I mean, the anatomical source of random structure in irises is an anatomical question, and there's a literature about that, but I'm just saying that these wavelets can produce any level of exact reconstruction that you'd like.
Any other questions? John
Sure.
made a convincing case
Okay.
about the uniqueness of iris
Thank you.
pattern information. What are the barriers to its wider deployment?
Thank you. Many barriers. First of all, since DDA is here, I will say that there's no legal, iris evidence is not legally admissible today. Yesterday from James Loudermilk's presentation, we learned that even though fingerprint evidence was admissible for a long, long time, still they were using human-based expert decision-making long after the automated AFIS system was outperforming. So that's one point in terms of forensics, given the focus this morning. There's no legal status to iris evidence. It would not be admissible in a court. Secondly, the popular culture is just so full of ignorant misperceptions about the iris. I mean, it's amazing. People believe that, for example, if a woman becomes pregnant, that changes her iris pattern and iris recognition will no longer work. Or that if all kinds of nonsense. If your personality changes from day to day, that affects your iris code. And there's a lot of superstition about the iris. And there are cultural practices, especially in Southern Europe. Iridology is a form of divination. Iridology is very popular in Mediterranean countries. It's popular in France as well. It's like reading the palm print, but it's a divination, a guessing about predicting the future from the iris pattern. There's a much bigger market for iridology than there is for iris recognition. I missed my calling. Anyway, so that's a short answer. And the press have not helped. The press are full of misunderstandings about the iris. It's full of nonsense. I'm sorry to have such a negative tone.
Any other questions? Yes?
I can try to speak up. Thank you for a nice presentation. Did you have a chance to find some numerical correlation between MTF resolution and recognized performance?
Yes, I've done a lot of studies of using lower frequency sampling of the iris and looking at, so that's MTF, the modulation transfer function, the range of frequencies that you use in encoding the iris, how that affects performance, and it affects the two distributions differently is the short answer. So lower frequency coding, focusing on the lower frequency part of the MTF, favors the authentics distribution because alignment of the patterns is less critical if you're looking at lower frequency structure, but it makes the impostors distribution wider, broader, which is bad, because you have less entropy. Entropy is higher in the higher frequencies. If you use higher frequency wavelets, more microscopic analysis, you improve the impostors distribution by making it narrower, higher entropy, but the authentic distribution suffers because you have to get quite precisely aligned. So roughly that's the answer. I think Joseph Biglin had a question.
So if there are no more questions, thank you.
May I show just one more slide about the vaccination program? By the way, this is the theology. The theology of iris recognition is the doctrine of suspicious coincidences. We'll come to that later, maybe in private discussion. But after summarizing the UID deployment and some of its failure modes, this is the last picture. Where is it? Sorry, here it is. So this is a pilot that is beginning now in Pakistan and India and in some African countries to overcome the fact that the vaccination records are unreliable, to try to use the iris code to, first of all, retrieve an identity from an iris code database, and having retrieved an identity, to access a clinical database to retrieve the vaccination records, because the timing of vaccinations is quite important. And all of these databases have to be resident in a portable device with no internet connectivity, that has no power, battery powered, and that can only be docked at the end of the day. These are the challenges of this vaccination deployment of use of iris recognition, which the Bill Gates Foundation is exploring now. Thank you for this last opportunity.
John, thank you very much for the
Pleasure.
fascinating talk.
Pleasure. Thank you.